Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our investigation of the topic of regression. If you recall from the previous video, we took a big step forward from just understanding if there was a relationship between two variables to really analyzing what we could use that relationship for, namely the idea of building a model and using that model for predictions. In this video, we're going to spend a little bit more time sort of developing that idea, talking about the type of model that we'll be building for this class, which if you recall from the previous video was called the least squares regression line, or the LSR. So let's talk a little bit more about that LSR and then take a look at an example. So remember, the LSR is a linear model, meaning that it tries to fit a linear equation to the data. If you recall from the previous video, we saw an example where after we had constructed the LSR equation from the calculator, we saw that once we graphed it on the scatter plot, it did indeed go through the general pattern of the data, fitting the data as best as possible. A couple notes, as we mentioned, we will often write the LSR with the notation y hat equals ax plus b, or if you prefer not to use the variables x and y, the response predicted, or response hat, equals a times the explanatory plus b. And remember that that choice of using that little hat notation there is just to indicate that the output of the model is a predicted value. And again, what that means is that it wasn't an observed value, it wasn't a data point, it was something that we're predicting entirely based on our model. Remember that in terms of constructing a linear equation, as we discussed in the previous video, there's two components that you need to understand: the slope, A, which tells us what happens to the y or response variable when we increase 1 unit in the x or explanatory. Keep in mind this little interpretation or understanding of the slope is actually the algebraic definition of slope. If you think back to when you sort of studied slope in an algebra class, you probably saw something like the rise over the run. Well, this is exactly the same idea. This is just saying that that slope value tells us what happens to the response variable when we increase 1 unit in the explanatory. The intercept, B, which is the second component that we need for a linear model, tells us what the predicted value of the response is when the explanatory, or the x value, is equal to 0. Again, from algebra, you probably remember that the intercept is the value where the line goes through the y-axis. From our perspective, it's the predicted value of the response when the explanatory is equal to 0. Now, I'm mentioning these things about slope and intercept because something we're going to start doing is interpreting the slope and intercept of our model. Once we construct a model, I mean, it's nice that the calculator can do it for us, it's nice that it fits the data, but we'd really like to say what these things mean in the context of whatever situation we're gathering data about. So again, remember that the slope is telling us about what happens to the response when we increase 1 unit in the explanatory, and the intercept is telling us sort of where the response starts off when the explanatory is equal to 0. Now, as a quick note about interpreting these, and we'll see this in action as we do more and more examples, is that when interpreting these two components, the slope is always going to make sense. Every time we build an LSR, we can discuss what the slope means and how it actually relates to the context of the situation. The intercept, on the other hand, may or may not make sense in the given context. This is going to depend on whether or not it makes sense for the explanatory variable to be 0. Sometimes it will, so there's explanatory variables where it's a very sort of normal thing that they could be 0. Other times it won't make any sense for the explanatory to be 0, so sort of correspondingly the intercept won't make any sense. So we'll just be careful of this when we're doing our interpretations. Sometimes you guys will be asked to interpret the slope and the intercept. Sometimes you'll be asked to just interpret the slope, because again, sometimes the intercept doesn't quite make sense. Still means it's mathematically correct, it just doesn't make sense in terms of interpreting and contextualizing in the situation. Remember also, last thing we sort of wanted to mention from the previous video before we get to this next example that'll sort of run us through all this, is that the main use of the LSR, besides sort of modeling the pattern, is to make predictions. Remember, the LSR allows us that if we have a value for the explanatory, we can use the LSR to make a prediction about the response value. Again, this is the whole idea that if you know that two variables are correlated, you can use the explanatory as a predictor of the response. And that's regardless of whether or not you have correlation or causation. It doesn't matter. We can still use it as a predictor. Remember, to make a prediction using the LSR, we will plug in a value of the explanatory variable and then use the equation to calculate the predicted response. So remember, when we're using that LSR, we're going to be basically plugging a value in for x or in for the explanatory and then calculating the y hat, the y predicted, i.e. the response or the predicted response there. Okay, so this was just a sort of quick summary of everything that we had sort of covered in the previous video about this LSR. Let's go ahead and take a look at one more example of putting all this stuff together before we then start to move on to talking more about what are some of the limitations or what are some of the things that we have to be careful about when making these predictions. So let's take a look at this example. Let's suppose that there's a food truck owner who wants to study the relationship between the number of customers they get each day and their daily profit. To do this, the owner records both of these variables for 9 randomly selected days. So they get the following data. So there was a day where they had 22 customers and they made a profit of $50. There was a day where they had 57 customers and made a profit of $200. There was like a day where they had 36 customers and they made a profit of $95. We're going to try to do all the pieces we've discussed so far with correlation and regression. We're going to draw a scatter plot for this, and then of course inside of there we'll also have to identify which is explanatory and which is response. Then we'll go ahead and calculate the correlation coefficient and use this to decide if there's enough evidence for a correlation. Remember, that's where we'll make use of that table E. We'll construct the LSR. That just means we'll find the equation for that linear model. We'll graph that linear model on our scatter plot to really confirm, oh, it does fit the data, which of course we know it does, but it's a nice visualization. Then we'll interpret the slope and intercept of the LSR. So we'll talk about exactly what does that A and B value mean in this context. And then finally, we'll predict the profit on a day where the truck has 40 customers. So we'll actually make use of our model. So let's go ahead and do this. To start off with, we want to draw a scatter plot for this data. So we need to identify which should be explanatory and which should be response. This should hopefully be becoming a little bit easier here, but of course we would think that the number of customers might impact the profit you make. It wouldn't make sense to say that the profit impacts the customers, right? Chronologically, that's sort of out of order. We think that the number of customers who show up should probably impact your profit. So this will be our explanatory, and that means when we go to type it in, we'll put it in L1, and this will be our response, which means that we'll go ahead and put it in L2. But let's first start off by drawing that scatter plot. So we'll go down here, and for A, let's go ahead and give ourselves our scatter plot. So remember, this will be our response, which we decided was the profit in dollars. And this over here will be the explanatory, which was the number of customers. All right, let's take a look at how we want to scale these axes. So for number of customers, it looks like the low end was 18 and the high end was like 57. So we could go by like 5s or something like that. Maybe we start at 15 or something, whatever is sort of easy to do. So we can go like 15, 20, 25, 30, 35, 40, 45, 50, 55, and I think we said the highest was 57, so we need to go just a little bit farther, and there's 60. Okay, so there's our number of customers. Now do keep in mind this has been condensed here, which is fine, because again, this really is everything from 0 to 15, which doesn't fit our scale of 5. All right, let's talk about the profits. It seems like the lowest profit was $45 and all the way up to 200. So again, we can sort of choose any scale that we like. Maybe we can start at like 40 and go by like 20s or something. So we'll say that that's 40, and then that'll be 60, 80, 100, 120, 140, 160, 180, and 200. So there we go. So we said we were going to go by 20s there. All right, so there we go. Is this part actually condensed? Yep, right, that would be like 40. That doesn't fit our scale, so we need to indicate that that part has been condensed as well. Okay, let's go ahead and plot our points. So we had 22 customers and a profit of $50. So 22 customers and a profit of $50. That will be right there. 33 customers and a profit of 125. So 33 and 125 seems to be up there. Then we had 29 customers and a profit of 45. So 29 customers, profit of 45 seems to be right about there. Then we had 46 customers, profit of 165. 45 and 165 seems to be somewhere up there. Oh, sorry, 46. Probably should move that over just a little bit. So it's 46 and profit of 165. So again, probably right about there. Okay, we had 18 customers and a profit of 60. So 18 customers, profit of 60, probably somewhere right about there. We had 57 customers, profit of 200, so somewhere way up there. Okay. 47 customers, profit of 135. 47 and 135 seems to be right about there. 42 customers and a profit of 150. So that would put us right about there. And then finally 36 customers and a profit of 95. So that should put us right about there. Okay. Again, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. What sort of general direction are we seeing? Well, it does look to be positive, which should make sense. The more customers you have, the higher your profit should be. So it makes sense that we're seeing sort of a positive direction here. We'll have to actually calculate the correlation coefficient to decide if it's a strong enough pattern to really be considered a relationship. So let's go ahead and do that. So for part B, we want to calculate the correlation coefficient. So now is the time to go ahead and type this stuff into your calculator. So if you're following along, you hit Stat and Edit, clear out anything that's in L1 and anything that's in L2. Then go ahead and put the number of customers into L1, so 22, 33, 29, 46, 18, 57, 47, 42, and 36. And then for the second list, L2, go ahead and put in those profits. 50, 125, 45, 165, 60, 200, 135, 150, and 95 there. Once we have all that stuff in, we can hit Stat, Calc, and go to that fourth option, which is that linreg AX plus B. Make sure you have it with L1 and L2. If you have the newer calculator, if you have the older one, you can just hit Enter again. And we'll go ahead and record the correlation coefficient, and you should find an R of approximately 0.9199. Notice that that is indeed positive as expected. Notice it is also pretty close to 1, so it's pretty strong. To confirm that it is really strong enough, though, we can go on to Table E with the N, the size of our data set, being 9, and we can look up that value, that critical value. So let's go ahead and do that. So we have N equals 9 right here. Intersecting that with our 0.025 shows us that our critical value has to be 0.6664. So our critical value here should be 0.6664. All right, we now need to do a comparison. We don't need the absolute value, but it's just good habit to write it. So how does the absolute value of R compare to this? Well, this would be 0.9199. That's certainly larger than 0.6664. So the R is larger than the critical value, which implies that we do have enough evidence for a positive correlation. So, in other words, this pattern that we're seeing there, it is a strong enough pattern to really believe that it is a pattern, that it's not just, sort of randomly happening or something like that, that we can really say that the number of customers that you have is associated or correlated or related, or however you want to phrase it, to the profit that the truck earns that day. All right, let's go ahead and actually build that model now. Now notice that part C really only makes sense because we successfully found evidence in part B. If we didn't find evidence for a relationship, we wouldn't model that relationship. But since we did find enough evidence, let's go ahead and build that model. So we want to construct that LSR. Well, we can get the A and B values from our calculator. If we go ahead and do that with a little bit of rounding, we should find that A is approximately 4.0 and B looks to be approximately negative 32.6. So I'm just rounding to one decimal place on both. So we can write that LSR as y hat equals 4.0x minus 32.6. Or if you prefer, you can say that the y is the profit. So the predicted profit is equal to 4.0 times the x, which is actually the number of customers, minus 32.6. So there we go. That's our LSR, right? That's our model that should best fit the pattern of the data that we're seeing here. All right, for D, we wanted to go ahead and graph the LSR on the scatter plot. Let's give ourselves a sort of fresh page to do that on. Of course, we could just do it here, but just to make it a little bit cleaner, I'll go ahead and copy this stuff, and so just so we can do the work on a separate page and not have to toggle back and forth. So let's go ahead and do that. So this will be part D here. Let's go ahead and paste that in. There's our scatter plot, and we'll get rid of that A there. Okay, and now let's go ahead and get those points. Remember, you're going to need 2 points. Let's also just copy over our LSR. Remember, our LSR here is y hat 4.0x minus 32.6, or the predicted profit equals 4.0 number of customers minus 32.6. Again, doesn't matter which expression you use. You can use the variables, or you can use the actual names of the variables, whatever you prefer. All right, so let's choose some values. So we need to choose 2 explanatory values. Again, I like to use the sort of ends of my interval. So we can try like plugging in 15 and 60. So let's maybe choose number of customers equal to 15, right? Because that would be on my low end of my interval there. So I'd get my predicted profit to be 4.0 times 15 minus 32.6. 4 times 15 minus 32.6 equals 27.4. Okay, now this is something we got to be very careful with. If we think about where that 27.4 is, that's a predicted profit. That lands in this sort of squiggly section, which has been condensed. So we can't really use this point. This is not a good point to use. So we're going to don't use this since it is in condensed area of axis. So that's okay. We don't really want to use that because 27.4, we might say, well, shouldn't it be somewhere like, really close to 40? But we don't have an appropriate scale because, again, that whole section has been condensed. So we're not going to use that one. Let's choose something else. Let's go just a little bit over. If 15 didn't work, maybe let's just try 20. Now, so let's choose number of customers equal to 20 instead. So that gives us then that the predicted profit should be 4.0 times 20 minus 32.6, and that looks like we should get 47.4. Okay, that one we can definitely use. 20 customers, predicted profit of 47.4. So if we draw that, 20 customers, predicted profit 47.4, looks like it should be right about there. Okay, and then we need another point. We can go down and use the other end. So let's choose number of customers equal to, say, 60. So the profit then should be 4.0 times 60 minus 32.6. So if we do that, that should give us 207.4. So that means for 60 customers, we should have an output of 207.4. So again, that'll put us just a little bit beyond where our axis ended up there. And then if we actually connect that, there we go. Notice that that line that we just drew, it definitely has a positive slope, indicating the positive direction, and it does seem to generally fit the pattern of the data here. Now, a couple things here. I wanted you guys to see a situation where you landed in that condensed section, and I generally recommend avoiding using those points. Obviously, if you had chosen a different scale for your axis, maybe this didn't need to be condensed, and then this would have been fine. There's nothing wrong with this prediction, 15 and 27.4. It just didn't land in a nice part for us to draw it on our graph. Of course, we could have redrawn the axis here and then, had a different scale, and it wouldn't be an issue. But I just wanted you guys to see that if you do have a predicted value that lands in this condensed section, you don't want to just go ahead and graph that because the scale will be off, the point will be in the wrong location. So we just went ahead and recalculated for a different explanatory. We chose this explanatory, and then we were able to connect those values. Once again, notice that there were some days where the cart sort of underperformed. Even though it had a good amount of customers, it didn't make as much profit as we would have thought. And there were some days where the the food cart sort of overperformed, right? It did better than we would have thought based on the number of customers. We're going to investigate this idea of sort of the difference between what really happened and the predicted value more as we continue on our investigation of regression. For now, though, let's turn to talking about these components, the slope and the intercept. So we'll talk about part E here. So we want to interpret the slope plus the intercept. So let's talk about the slope first. So if we remember the value for the slope here, which we'll just do in green, that's this guy right here. That's that 4.0. So the slope is 4.0. What does the slope mean? Well, remember it always is going to be that as we move up 1 in x, this value for the slope is what happens to y. So in other words, we go up 4.0 in y. Now, what does it mean to go up 1 in x? Well, that means, what is our x? Our x is our explanatory. It's the number of customers. So when we go up 1 customer, we're expecting to go up 4.0 in terms of the profit. Now what we'd like to do is write that as an actual sentence rather than this sort of weird notation. Let's actually just say what this means. We're saying our model predicts that each additional customer will yield an extra $4 of profit. Notice that when I go to write this interpretation, I make use of the units. How were we measuring profit? It was in dollars. And notice that this makes sense. We're basically saying that our model says that each extra customer basically translates to roughly $4 of profit. This doesn't mean that every person is identical and is going to always give you the same profit, but it's sort of telling us what the general pattern is. Each person that shows up seems to give us roughly $4 of additional profit. All right, let's go ahead and talk about the intercept as well. So the intercept is this value, the negative 32.6. So the intercept here is the negative 32.6. What does the intercept mean? Well, remember algebraically, the intercept means that when x is 0, y is negative 32.6. So what does x being 0 mean? That means when your customers are equal to 0, your profit is supposed to be negative 32.6. Now, negative profit might not initially seem to make sense, but keep in mind a negative profit would be a loss, right? It'd be losing money. Does it make sense to lose money if nobody shows up as a customer? For sure, right? You probably have some fixed costs like paying employees or ingredients or whatever. That's definitely going to contribute to a loss if no one buys anything. So we would say our model predicts that if the cart has 0 customers, it will lose $32.60 that day. So, in other words, this basically tells us if nobody shows up to this cart or this truck, they expect to lose about $32.60 that day. Again, notice that that makes sense because having 0 customers is possible. Right? Again, there's going to be situations where we won't talk about the intercept because it doesn't make sense, but this is a situation where the explanatory could be 0. Having 0 customers is certainly possible, so we were able to write an interpretation for that. So, Couple things to keep in mind with interpreting slope and intercept. Notice that this component about x is always going to remain the same. Every time you talk about slope, it's always going to be about as you go up 1 in x, and every time you talk about intercept, it's always going to be about when x is 0, or when the explanatory is 0. The part that changes is about the y, right? The slope tells us what happens to the y when we change 1 in x, and the intercept tells us what y's value is when x is 0. So these parts of the interpretation will never change. This is the part that changes based on the values you actually calculated. All right, let's wrap this up with one final part, part F here. We want to go ahead and predict the profit on a day where the truck has 40 customers. So 40 customers, how do we do this? Well, and we want to know the profit. Well, that's the value of the explanatory variable. The customers were the explanatory, so we can just plug this in. So our predicted profit is equal to 4.0 times our explanatory, which is the 40, minus that intercept, which was 32.6, right? That was our model. We said 4.0x minus 32.6. In this case, we're saying we had a day with 40 customers, so plug that in. And we should get that the predicted profit here, if we type that in, 4.0 times 40 minus 32.6, we should get 127.4. So we predict that on a day with 40 customers, this truck should make around $127.40 of profit. So there we go. We're saying that's our prediction. If we had 40 customers, we think that we should make somewhere around $127.40 of profit. So again, this is really our ultimate goal with this building a model, right? Is to be able to make predictions, right? And if you imagine, you know, owning like a truck like this, right, you could then think about how you could use this to sort of set a baseline for how many customers you would need to get to actually make a reasonable profit for yourself, right? If this is what you expect to get with 40 customers, you could then determine, is this going to be enough? Is 40 customers a day doable? Do we need to get more customers, etc., right? So building a model here allows us to then make predictions about values of the explanatory that we might not have observed, right? There was no data point where we actually had 40 customers. We had things around there, but now we're able to extend our knowledge beyond just these 9 data points and actually have a model in general for this food truck, its customers, and its daily profit. Okay, so in our next video, we'll go ahead and we'll talk a little bit more about making predictions. We'll talk about some of the things we need to be careful with, some ways of understanding what we were discussing here, which is that, you know, on certain days of our actual data set, maybe the truck underperformed, on certain days it overperformed. We'll start to get a little bit more specific about the real background of what's going on when we're making these predictions.